right? They're going to come back together. So it's kind of like that couple that hooks up and breaks up, hooks up and breaks up, and you're just like, freaking make up your mind already, right? But that's what water is, right? It's the Elizabeth Taylor and Richard Burton of the chemical world. You guys probably have no idea who that is. Elizabeth Taylor and Richard Burton. Or somebody's got to know. Right? They married each other 4 or 5 times. Elizabeth Taylor and Richard Burton. Okay, so water is amphoteric, which means it is both an acid because it increases the hydroxide or hydronium concentration, and it increases the hydroxide concentration, which makes it a base. So it's both. Okay, this effectively makes it a neutral solution as well because its pH is going to be exactly 7. It's right in the middle. It's producing both things. But it's not just neutral, it's also amphoteric, which means it can act as a base if it wants to, and it can act as an acid if it wants to. And I say want to, but that's needlessly anthropomorphic. It's not that it wants to. In the presence of an acid, water will act as a base. In the presence of a base, water will act as an acid. We'll talk about that when we talk about Bronsted-Lowry in a second. Bronsted-Lowry. I'm just rewriting this because it's hard to read the pink up there. Sorry about that. Okay? Bronsted-Lowry. Bronsted-Lowry said, well, since water does both of these things and not everything's necessarily going to produce hydroxide, like what if we have bases that don't have hydroxide in them, right? Well, the answer is it's still going to produce hydroxide in water. But Bronsted-Lowry were like, well, what if you don't want to have an aqueous solution? What if you just want to look at the thing outside of an aqueous solution and see whether it's an acid or a base? And they said that an acid is something that gives away hydrogen protons. Okay? So it is a hydrogen proton donor. Okay? It has extra hydrogen protons and it will give them away. You guys follow? Right? They also say that bases are hydrogen proton acceptors. They will take them from acids. Okay. So let's go back to what Arrhenius said. Arrhenius said that bases have those OH negatives. Will an OH negative take a hydrogen from an acid? Yeah, absolutely, because it's negative and the proton's positive. So technically speaking, from that point of view, take a look at any anion. What if I wanted a chloride ion? Okay, would that be a base according to Bronsted-Lowry? Would it accept a proton?
Yeah, sure.
Yes, because it's got a negative charge. The proton has a positive charge, so it's a proton acceptor. So technically speaking, under Bronsted-Lowry rules, chloride would be what is called a conjugate base. It's a base that will accept a hydrogen proton. Yes, any anion would then accept a proton. Okay, and it's not just chlorine; it would be fluorine or oxygen. Like any of your negative anions would end up being bases. Okay. Now, a conjugate base is what would be left over after an acid gives away its hydrogen. Because if you give away a hydrogen, what are you going to be left with charge-wise? A negative charge. And so if an acid dissociates in water, it's going to be left with a base, a base ion, because there's going to be a negative left over. Imagine hydrochloric acid. Imagine hydrochloric acid, okay? Hydrochloric acid breaks up in water. You end up with an H plus and a Cl minus, okay? An H plus that gets donated is behaving as a what?
Acid.
An acid, right? And the Cl minus is going to act as a what? A base or an acceptor, okay? And we would call this a conjugate acid-base pair, right? Okay. So that is the word conjugate, the conjugate acid-base pair. The base is what is left over after an acid gives up a proton. Does everyone follow me there?
Are we going to conjugate acid and bases?
Well, it's a conjugate acid and base pair, but you don't. Do you know that there's a competition called a pun-off? I have a friend going to a pun-off, and it's a gathering, and it's apparently a huge gathering, like thousands of people, and they pun at each other all day. It's like my husband's worst nightmare.
Let us watch it.
Let us watch it, guys. Okay. You should go to the pun-off.
Penitentiary.
It sounds like a penitentiary, really.
No.
Is it?
Sounds like a punishment.
Wait, don't change it.
That's what he said.
Oh,
Then
it's
it's a punishment.
No.
It ends up a
laughing, be a fitting.
A proton, so a hydrogen, right? Okay.
What did you say? Proton or proton?
A proton? A proton is the hydrogen without its electron. Right? So, guys, and I just want to make sure everybody's clear. When I say a proton, we're talking about a hydrogen ion, because a hydrogen ion has lost what? A hydrogen atom. Take a look at a hydrogen atom. What does it have in its nucleus? One proton. How many electrons does it have? Well, one electron. If it loses that electron, then it's just a proton. Okay? So when we talk about H+, we're talking about a hydrogen proton. Okay? And we call it hydrogen because if there's only one proton, it's 1 on the periodic table, which makes it have to be hydrogen. Okay? All right. So Bronsted-Lowry and Arrhenius, did they disagree?
No.
Not really, right? So because when you look at it, the OH that Arrhenius said were bases would be a proton acceptor by Bronsted-Lowry's definition. So the two definitions kind of complement each other. It's kind of like saying, I'm going to give Nick a bicycle. Okay? Now, did I lose a bicycle or did Nick gain a bicycle?
Well, you can put it two ways.
Both, right? You could put it either way. And so Arrhenius's definition is like Nick gained a bicycle, right? And Bronsted-Lowry's definition is like I lost a bicycle kind of thing, right? And so you're looking at the same thing happening, it's just how do you define it? There's two different definitions of what is an acid and what is a base, okay? Now, what was very interesting is Lewis came along, and Lewis, of the famous Lewis dot structure, was obsessed with electrons. And he said protons don't have anything to do with it. You're either accepting or donating electrons, not protons, okay? So it's kind of like saying, from the point of view of the bicycle, did the bicycle lose an owner or gain an owner? So it's just a more complicated way of looking at the same thing. For that reason, I'm deciding to leave out the Lewis definition of acids and bases, because he just wanted to look at negative charges instead of positive charges, okay? I'm going to stick with the positive charges because it's the one thing that the Bronsted and Arrhenius definitions have in common, okay? You guys with me on that? If you go to AP, understand that Lewis definitions of acids and bases, Lewis just called it electron donors and electron acceptors, except for that acids do what with electrons? They accept them, and then bases donate them, because you're looking at the negative charge, so he just wanted to look at everything in the reverse way, okay? All right. So let's take a look at what happens when you put an acid in water and what happens when you put a base in water, from both of these points of view, okay? So in this first case, we have hydrochloric acid. It is an acid because when it breaks apart, you're going to break it apart into what? H plus and Cl minus. Okay? All right? So with this being an acid, what is it going to do?
It's going to act as a...
It is going to act as an acid. It is going to donate its hydrogen. So the water is going to do what? Accept it. Now, how does that happen? And in order to see why that happens, we have to look at what water does. Like, water is polar, right? So you have this negative space and these positive spaces. Okay, Gage, I certainly hope that you were taking notes over there, because that doesn't look like notes. because there's a camera on behind you, right? So what does water do? As a polar molecule, okay, you have water, and if this acid is donating a hydrogen, what is this water going to do? It'll accept it, right? And where is this hydrogen going to go? Okay. On that left side, right? And so the water becomes a hydrogen acceptor, which means that it is acting as a what? It's acting like a base. All right? So you end up with this water that has an extra hydrogen stuck to it. We call this a hydronium ion. This is something you need to know. Hydronium. It is a water that has an extra hydrogen attached to it. Now, is this going to be a stable molecule? Does it want to really be this way?
Not really.
Not really, because while it's polar and it does attract that positive charge, it's not like that's going to be a really strong covalent bond, okay? So that's an ionic bond, and this is covalently bonded. So you have a covalently bonded water that has an ionic hydrogen kind of stuck to it, okay? Sort of. But this is a completely reversible ionization reaction, okay? And then your chlorine is going to act as what here?
Yeah, base.
This is going to be a base. Because what would it do? If I put a hydrogen next to it, what would it do?
It's accepting it.
It would accept it. This guy would do what with the hydrogen?
Give it, kick it out.
Would give it away. Because this water is like, I'm a water, what do I want with a third hydrogen? It would donate it. So this is an acid. Okay?
What type of like? What would that water be?
Hydronium?
Yeah.
Hydronium is simply, and specifically it's called a conjugate acid and a conjugate base. And it's just what happens when you put acid into water, okay? What's interesting is when you put acid into water, what you have is all four of these substances, okay? Because these guys are also going to be attracted to each other, and they're going to exchange ions and become this again, okay? This is kind of like being in high school, okay? You always have people that are hooking up and breaking up and hooking up and breaking up, and you guys hook up with other people. These guys hook up with other molecules, and these guys break up, right? And in this bottle of water, you have all of these things happening all the time. You have water that is OH, you have water that is H, you have water that is H3O, you have water that is OH, you have water that is H. You have water that is H2O, believe it or not. There's actually H2O in here. But amid that H2O is all these pieces of water that are breaking up and hooking up. And it's kind of a back and forth process. Okay? So let's take a look at what happens if you put a base in water. So here we have a base. It is a nitrogen with 3 hydrogens. Okay? So which means it has a lone pair, and this is a polar molecule. It has a negative end, okay, and a positive end with all these hydrogens. Okay? What's it going to do as a polar molecule with a specifically negative end? What is it likely to do?
Accepts it.
It's going to accept. And you can look at this other side if you lose track of like what's going to happen. It's going to accept a hydrogen. Where's that hydrogen going to come from?
The H2O.
The H2O, right? So H2O becomes a source of hydrogen. So what's going to be left over? Okay. Hydroxide. Okay? You guys with me? So hydrogen, or water becomes a hydrogen donor, which makes it a what? Donor?
Acid.
This makes it an acid. Okay? So then on this side you end up with your NH4 plus. It has an extra hydrogen. What would that make this?
But then when it is an acid and it gives that up, couldn't it be a base again?
Well, because the OH is left over, it turns into a what? This becomes a base. By both Arrhenius's definition and Bronsted-Lowry's definition, OH is a base.